Alright, hi guys. I just thought instead of me going through this in class, I might just go through the SAC on this video here. And I'll insert little chapters, one per question, so you'll be able to skip along to the question that you are not sure about. And you can check how I would go through it, my thinking on it. Obviously, you're welcome to look at the whole thing if you want, but at least look at those questions that you missed. Okay, so this is the transmission SAC that we did just before the holidays. It was worth 30 marks, you had 70 minutes. I think overall most people seemed to finish, which was good. So it looked like that was enough time. And overall I've been pretty happy with how you've gone. Obviously there's a few things here and there, but overall I'm very happy. Okay, question one. Question one was Estelle was setting up this generator and she was going to operate it by hand. And this information comes up a few times in the first 5 or 6 questions. That the magnetic field being generated by these magnets here is 0.5 Tesla. And the coil has an area of 0.6 meters squared. And she's wound the coil around 20 times. All right. So find the maximum magnetic flux through each turn of this coil. People did pretty well there. It's just going to be the area of that coil times the magnetic field strength. The only thing is that each turn. So we're not caring about the fact that we're going around 20 times. Just one turn worth here. So that's going to be... so we're going to start by stating the formula on the top line. Always a good idea to do that. That way if you do make a mistake, you still might pick up some partial marks because they know that you're heading in the right direction. So we get, in this case, 0.5 Tesla times 0.6 meters squared. Beautiful. And phi eventually equals 0.3 Weber, whatever you want to call it. Yeah, most people did that pretty well. So moving on to question 2. Question 2 is hard. Question 2 is Estelle has not yet got the hang of the hand crank and twists it in a stop-start motion. So she produces this flux here, and we want to take this flux graph and turn it into an EMF graph. Right? Now, the important thing to notice here is, or the important thing to realize, is that the EMF is going to be the gradient of this graph. So every time the gradient changes here, we're going to expect the value of the EMF to change. Whenever the gradient is 0, i.e. this graph is flat, we're going to have 0 EMF, and most of you picked up on that pretty well. And the last thing is that we see that the gradient changes sort of instantaneously at these points here. So it's going to be fine if the EMF changes instantaneously there too. Now, in real life, things don't change completely instantaneously like that. There'd be a bit of a curve, so if you put a bit of a curve in your graph, that's fine too. But because these are vertex type points, we're going to allow for step changes in the EMF, sudden changes, right? Okay, so let's go about drawing that. First off, I'm just going to draw in just the 0 parts because they're kind of easy. So there we go. There's 0 between there and there. Let me make that a bit thicker. Right, we're going to have 0 there, and we're also going to have 0 over here when it's flat again over here. So we're not saying the flux is 0, but the flux isn't changing, which means the EMF has to be 0. Okay, then the next thing is we've got a positive gradient here, and remember we don't have to worry about the scale, so we're just going to put some positive EMF in up here, and obviously I've misspoken there, but I'll fix that up in a sec. So the gradient is something, it's 5 up for 1 across, let's say. Right, so we're going to have an EMF of, let's say, 5 volts. But because this is a positive gradient here, we're actually going to have a negative EMF. So we're going to put the EMF down here. Okay, so a few of you lost a half or 1 mark for not remembering to do that negative part. Then if we look at the next phase where we've got a non-zero change in flux, we've got this downward bit, and this looks about the same gradient as this, only now it's negative, which means the EMF will be positive. So we should have sort of this again, but positive and for a longer period of time, because it goes that whole time there. And then we have a positive flux bit, sorry, a positive change in flux, which means a negative EMF, and it's a little bit lower gradient, so we're gonna have maybe there. Okay, don't worry too much about your scale, but that's what the EMF is going to look like over time. It's going to have these sudden changes. It's going to be negative, and then it's going to be 0, and then it's going to be positive, and then negative, and then 0. If you wanted to link those up with a kind of a bit of a curve, that would be fine as well. Now, we had some people sort of just have a line that shoots down to this point, comes back up to 0, shoots up, comes back. Make sure that your line here matches the gradient above, not just at every point. So the gradient at t equals this particular value here is a certain value, which means the EMF is that value down there. It's not just that the EMF will reach that value at some point, it's at each time, whatever the gradient is, the EMF will follow. Okay? So that's question 2. Your answer should have looked something like that. Okay, question 3. Estelle eventually gets the hang of it and moves the crank in a smooth, continuous fashion to produce AC electricity. So AC given by this sinusoid here, as demonstrated in the induced EMF graph below. She uses a gear system to generate such high turning speed, because we can see she's turning much faster than a human could speed that. Okay, we're going to find the period and the frequency. Okay, so once we found the period, the frequency will be easy. It'll just be the inverse. The period is going to be one full sinusoid here. So it's going to be from 0 to 0.005. So period equals t equals 0.05 seconds minus 0.00 seconds equals 0.05 seconds. That's going to be our period there. And then the frequency, by definition, is just 1 over the period, which means we're going to get 1 over 0.05 seconds equals, well, 1 over 0.05 is 20, and 1 over a second is a hertz. So we get 20 hertz there. Most common mistakes here were to maybe only take half and use 0.025, or to just completely misread this label here. Actually, the most common mistake was to say that this was 0.5, not 0.05, which is, yeah, I suppose it happens, but just make sure you're carefully reading your scale there. I didn't trick you this time, but quite often the VCA will try and trick you by putting in milliseconds or something over here. So just make sure you're aware of what's on the graph labels as well, the axes. Okay, question 4. Question 4. Using the data given on the original statement and the period calculated above, estimate the average EMF produced by 1 quarter cycle of the generator. So if we want to find average EMF, then we're going to have, I can't do a fancy E on here, so I'll just write EMF. It's going to be negative N, so that's Lenz's law, and then N for the number of coils. That's going to be that 20 we talked about earlier that we didn't use in the first question. And then it's going to be change in flux, and that's going to be divided by the change in time. Okay, so N is going to be 20. Change in flux, well, it tells us to do a quarter cycle here. So a quarter cycle is going to be, we're going to go from this position here where we have a maximum amount of flux to this position here where we have 0 flux, or vice versa. But I'm going to use that one because you'll see in a minute it'll give us a positive number. Right, so if we're going from B times A to 0, then that's going to be a change of negative B times A. So we got negative, and we worked out earlier B times A was 0.3 Weber. Right, that 20 doesn't have any units on it because it's just a number of turns. You could write 20 turns and then you could call this 0.3 Webers per turn, but then the turns would cancel out. Right, and then lastly we're going to divide by Well, it's not going to be a full period because we're only talking about a quarter cycle. So it's going to be this number here divided by 4. So that's 0.0125 seconds. Right, and then finally we plug all that in, and we might have to get out our calculator at this point. I don't know what that is off the top of my head. 20 times 0.3 divided by 0.0125 gives us 480. So 480 volts. Okay, so question 5, it says you can assume that average EMF we just calculated is pretty close to the RMS value, and then it's asking us to find the peak value. So we're just going to use the relationship between peak and RMS. So V peak equals square root of 2 times V RMS. So that's just going to be square root of 2 times 480 volts, and that comes out to, there we go, 679 volts. Now, if you round it off any more than that, you'd probably start to lose a mark, but if you put a little bit more detail in, a few more decimal points, that's also fine. Remember, in Unit 3 and 4 physics, the amount of decimal places isn't specifically said you have to use this many. It's what's reasonable. So it would be unreasonable to throw out more information than that. It'd be reasonable to maybe keep a couple more decimal places, but nobody cares about the 5th decimal place on voltage. So you just have to have a bit of common sense about that. Okay, question 6. Estelle connects her generator to run a series of Christmas lights. She's still able to turn the crank at the same rate, and that's going to be important for question 7. But to her surprise, it's much more difficult than before. Now that the switch is closed and the lights are on, and we have to explain why. And people answered this pretty well overall, I thought. I was actually impressed. I think maybe there was a video going around with something similar in the revision, so obviously people took note of that, and well done. I was intending for this to be the really difficult question, so I was actually really pleased with the way you guys answered this. There's kind of 2 different ways to answer it. One is hard and one's easy. Let me take you through the hard one first, but this wasn't the one I was sort of intending for people to use, but a lot of people went with this in the end. The hard version of this is to say, and I'm going to structure my answer with dot points, because I think you should. And remember that we're going to start with what's happening, and we're going to end up with the thing we're trying to explain. Okay? So let me just... Hard version of this is we've got a current flowing, right? Now that the switch is closed, right? Before the switch was closed, we didn't have a current flowing. Now we do. Okay. The current will be flowing through the generator, which includes a magnet, and hence we'll feel a magnetic force, right? Because this is an induced current, according to Lenz's law, this current will oppose the changes that Estelle is trying to make. So we're going to get a force which is acting against Estelle, and I haven't necessarily worded this in the best way, I'm sorry. It's going to act against Estelle's motion because that's what induced currents do. Okay, so we're going to say closing the switch is going to allow a current to flow. That current is going to flow through the generator itself, and hence it's going to feel a magnetic force. And then we say, well, does that magnetic force help us or does it hinder us? And we say, well, Lenz's law tells us that it's always going to hinder us. It's always going to be against us. Hence, there will be an magnetic force opposing Estelle's applied force, making it more difficult for her to turn the crank. I would always end with some sort of summarizing little sentence there saying, how is it that the things I've said above prove the thing that I'm trying to explain? Some of our explanations, and I think I still gave people 2 marks if they didn't kind of wrap it up with a nice bow, but some of our explanations kind of just throw some facts out, some physicsy facts that seem vaguely relevant, and hope that they hit the mark. And that's, I mean, it's better than nothing, but we really want to structure them in such a way that we get from, here's what's happening, here's some physics, this causes this, causes this, causes this, and end up with, therefore, the thing that has happened had to happen. Okay? Now let me give you the easy version of this, which is, the easy version of this is that instead of conceiving this in terms of currents and forces and stuff, we can conceive of this in terms of energy. Okay? So, let me do that. When the lights are on, when the switch is closed and the lights are on, they are using energy. Okay? Energy conservation tells us that this energy must come from somewhere. Alright, it can't just be appearing out of the ether. Not that the ether exists, as we'll talk about later. It must be provided, right? Estelle is providing this energy to the circuit. If it is using more energy than before, then Estelle must be doing more work. Okay? So you can think of the word difficult isn't well defined in physics, so it can be taken as she's having to apply a bigger force or she's having to do more work, and because those two things are closely related, they end up meaning the same thing in this context. Okay? Either of those ways would have got you the full marks, and both of them are actually functionally equivalent. To say she's doing more work is to say that she's moving the same distance against a greater force. Work, in the simplified version, is just force times distance. So if she's applying against a bigger force, then she's going to be doing more work. They mean the same thing. Okay. Question 7 was pretty closely related to question 6, so if you've just skipped to here, maybe look at the question 6 one first. But question 7 asks, will the EMF measured across the generator be larger, smaller, or the same as when the switch was open? Now, you might... people sort of talk themselves into a corner with things like back EMF and thinking that, well, the lights are kind of stealing some of that voltage, so maybe there's going to be less voltage there. The thing to bear in mind, there's a really key sentence up here that you might have just glossed over, but she's still able to turn the crank at the same rate. So what that means is that the period of rotation is unchanged. And remember, if we're thinking about a generator, we've actually got a formula for what the EMF is. It's negative NBA 4 times the frequency. And so if none of those things have changed, then the EMF hasn't changed, right? So we've still got the same generator with the same N, the same B, the same A, and then the only thing that might change is the frequency. So if it gets more difficult, maybe she goes slower, and that really would reduce the EMF. But if we're saying that she's able to crank it at the same rate, then we're saying that that frequency hasn't changed, which means none of those parameters have changed, which means the EMF is going to be unchanged. Some people struggle with that conceptually, I think. I think that is a difficult thing to get your head around, so I'm just going to write same there. You didn't really need to explain it. You could just write same, because it's only 1 mark, and the question just directly asks what is it? But the thing to think about here is think about like a 1.5 volt battery. Now, a 1.5 volt battery has an EMF of 1.5 volts. If you put a voltmeter on it at either side, you're going to get 1.5 volts. It doesn't matter whether it's connected up to a circuit or not. If you connect it up to a circuit, it's going to be providing 1.5 volts to a lot of electrons, which are moving through each of them, picking up that 1.5 volts and then dumping some power in the circuit, etc. Or it can have 1.5 volts and have no current going through it. Voltage is a separate concept from current, and we've really got to be clear about that. So EMF is how much potential, and the word's there in that potential, how much potential energy could it provide to an electron if an electron were to pass through it. So even when that switch is open, it's still providing EMF, it's just not actually generating a current. And then when we close the switch, we get a current through it, and it's providing that same amount of EMF, it's just providing it to a lot more electrons now. Okay. All right, question 7. All right, question 7 was the start of the big transmission problem, which I told everyone leading in, there's going to be. Sorry about that. I told everyone going in, there's going to be a transmission problem on there. And generally speaking, it was pretty well done. If you didn't do so well on this transmission problem, it is really worthwhile looking back on. I suspect it's going to be on every exam while this study design holds, there's going to be a question like this, because they've put it in as a specific outcome on its own, as in, can students tell me how an electrical transmission system works? So if you haven't got this down, then this is the thing to concentrate on, okay? So this is sort of question 8 through 12 or something like that. Make sure you can nail those questions. All right, so the first question answers what's the RMS current in this, in the generator section of the circuit. So first off, you've got to be able to differentiate between the different sections of the circuit. We've got this circuit here, which is the generator section, and then we've got this in the middle, which is the transmission section, and then we've got this on the end, which is the load section. And each of these is its own separate little circuit, right? So we've got a closed circuit here, and a closed circuit here, and a closed circuit here, and then they're linked. Energy is provided from one circuit to another via these transformers, okay? So what's going to be the RMS current in the generator section of the circuit? Okay, well, we just have to look at what information do we have about what's going on in that circuit. Well, we're told that the generator is putting out 10,000 watts at 500 volts. So we say, oh, well, do we have a formula that links those two things? Yes, we do. We know that power is equal to current times voltage, right? Now, in this formula here, if we want to talk about power, then we've got to be talking about RMS and RMS, okay? The relevant currents and voltages for power are the RMS currents and voltages, okay? But they are actually the ones that are, in almost all cases, going to be provided to us. So if this says 500 volts peak here, then we do a conversion, but for the most part, you're actually going to be given RMS values, okay? So we just have to plug in P is 10,000 watts, and I is the thing we want to know, and V is 500 volts. We could put RMS on that, just to be clear. Right, and then we'll do a bit of rearranging, and we get that the RMS current in there is going to be 20 amps. Okay, you can get out a calculator and check that for me if you want, but I think it comes out to 20 amps. Yeah, so that's that first part. All right, question 9. Question 9 says, what would the RMS potential measured across the secondary coil of the step-up transformer? So first off, we're going to say which is the step-up transformer. It's the one where the voltage goes up, which is going to be this 1 to 20, not the 20 to 1. And we're being asked for the secondary coil, which is, okay, that's the unpowered side. So this side's the powered side, that's the primary side. This secondary side is the one that's receiving the power. Okay. Well, we know that the potential is going to be stepped up by a factor of 20. Right? So if we have 500 volts and we step it up by a factor of 20, well, we get, let me write this out more formally, but V primary divided by N primary equals V secondary divided by N secondary. Right. And then in our case, we can just plug in some numbers. On the primary side, we have 500 volts, and we have, well, 1 turn or whatever it is. It's going to be 20 times less than the other side. And on this side, we have X and 20. So we end up getting V secondary equals 10,000 volts. Okay. I've kind of made that more mathematically opaque than it needed to be, but we just need to multiply the voltage by 20, right? Because we're stepping it up. Okay. So we got 10,000 volts there. Okay, then we want to find the power loss in the wires. Now remember when we're talking about power, sorry, I forgot to put a chapter note in there. One sec. Okay, question 10 asks us to find the power loss in the wires. Now, in all of these transmission problems, we're always going to assume there's no loss in here, there's no loss in here, and that all the loss happens in the wires themselves. Okay? Now, we've been told that our wires in total have resistance of 60 ohms. Sometimes they'll say it's an ohm per meter and it's 300 meters one way and 300 meters back the other way, and you've got to do a bit of working out there. But we're just told here it's 60 ohms. Okay? Now we want to find the power loss inside these. Now it's tempting to just say, well, power loss is V times I, or V squared on R, but the voltage that we know over here is the voltage between this point here and this point here. That's what we just worked out, was that 10,000 volts. That's not going to be the voltage dropped on that resistor. The voltage dropped from that resistor is hopefully going to be much, much less than that. So we don't actually know V across that resistor. All we know at the moment is the resistance of the resistor. So we need to work out what the current is. The way we're going to work out what the current is through it is we're going to take the current through this section and we're actually going to step it down by a factor of 20. So if we had 20 amps over here, then we're only going to have 1 amp going through here. So if the voltage got stepped up, then the current had to get stepped down by the same factor to conserve energy. All right. So that means we'll just state that current in transmission is 1 amp, right? And then now we can say that power loss is always equal to I squared R. So we're always going to use I squared R when we're talking about power loss. It's too dangerous to try and use IV or anything like that. You're going to make mistakes. Okay, so I squared R if we're talking about power loss, which in this case now becomes easy. That's 1 amp squared times 60 ohms equals 60 watts. Okay, and notice that that's a small number, and that's what we're hoping for. You should always check that what you get here is small compared to the total amount of energy being produced. So if we've got 60 watts out of 10,000 watts being lost, then we're doing pretty well. And that's the whole point of having this transformer system. So we're looking good. All right. So now we want to find how much power is available to the farm. Well, if we're saying that the only power lost in the circuit was lost right there, then that 60 watts is all that was lost. So P load is going to be equal to P generated minus P lost. So that's going to be 10,000 watts minus 60 watts equals 9,940 watts. Okay. People kind of wrap themselves up in knots, or most people did that pretty well, but some people wrap themselves up in knots trying to find much more complicated things than that, but it really is that simple. Obviously, we're using a simplified model of a transmission circuit here. In a real circuit, there are some losses inside the house, inside the generation, inside the transformers, etc. But in our model here, we're only having energy lost in those wires. Okay, question 12, find the potential available to the farm. A few different ways to do this. We know that the farm's getting 9,940 watts, and we actually know that the current inside that area here is going to be, well, if there was 1 amp going through here and the voltage got stepped down by a factor of 40, then the current must have got stepped up, so there must be 40 amps going around in here. So we could actually say that the farm is using 9,940 watts, and that's got to be equal to whatever current it's getting times whatever voltage drop it's experiencing, in which case that would be 40 amps times some unknown V. We can do that. Let's work that out. V equals 9940 watts divided by 40 amps. I don't know what that is. Equals 248.5 volts. Okay, so that was done pretty well overall. That's not necessarily the approach that everybody took. The other big approach that people took was to say, okay, well, I had 10,000 volts getting pumped out here. I lost some voltage across here, and they would work out how much the voltage lost there. And we can quickly do that. We can actually do that in our heads. We've got 60 ohms and 1 amp running through it. So we're going to lose 60 volts across here. So we're going to have 9,940 volts here. And then we're going to step it down by a factor of 40. But we literally just did that. We just did 9,940 divided by 40. And that's exactly what we got. And so we get 248.5 volts on this end here. And because this is a loop with nothing else in it, if there's 248.5 volts getting produced here, that must be what's getting lost on the farm. The only big mistake that I saw people make was forgetting to minus off the 60 volts here or the 60 watts here, and just acting as if nothing was lost in the circuit, and then we get 250 volts on the load. Not the worst mistake in the world, but yeah, you have lost a little bit of voltage in there. Right. So one thing to remember here is sort of a general rule you can take is that power gets lost, voltage gets lost because voltage is sort of a measure of energy, and so is power, but current never gets lost. Current is sort of perfectly transformed up and down through these transformers, or at least we're going to assume it always is. Okay. So yeah, so that run of questions from question 8 to question 12 is really the most important section of the test. If you've nailed that, then you've sort of set yourself up to do well on the exam. Because as I say, I'm 80% sure that there'll be questions like that on the exam. Okay. All right, let's move on to the next sort of little section. In this section, we've replaced the wind turbine with some batteries because there's no wind on this day. So she replaces the generator with a series of old car batteries, and so we've still got 500 volts on there, but it's DC now, not 500 volts RMS. And it's still putting out 10,000 watts apparently, at least at first, or this is the idea that she's looking for. But she finds that her farm is without any power, and we need to explain why. This question was overall pretty well done, but suffered a little bit from people sort of talking themselves around in loops. This is one that really benefited from using dot points and just saying this is this, then that causes this. Okay, so let's try and dot point out some answers. All right, what do we know? We want to go from what we know to the thing we're trying to explain. So if we're going to have some dot points, they're going to sort of, we're going to have dot point 1, dot point 2, dot point 3, dot point 4, dot point 5, dot point 6, whatever it might be. And the last thing we're going to say is, therefore, no power is available to the farm. There you go. So we're trying to get to that. And I like to put in that sort of last statement first so that I know I'm not done until I've explained that fact. Okay? So we've got a DC power supply, right? So a DC power supply puts out constant current in the same direction. Okay, that's key. That current is going to pass through that primary coil of the transformer, and it's going to produce a magnetic field. Right? This current passes through the primary coil of the step-up transformer and creates a, and here's the key word, and you might want to underline it or make it bold or write it a different color, constant magnetic field in the coil. Okay, and the fact that it's constant is key. Right? The fact that it's constant means the secondary coil experiences a magnetic flux from this field, which is unchanging. Right? So we have a non-changing magnetic flux. And then you might want to, this is where you sort of want to make the contrast to AC. You know, it worked before, it doesn't work now. What's going on? You want to say, if the current were AC, this flux would be constantly changing. Right. And then we're going back to DC because we want to keep our focus on the thing that's actually happening, not the thing that's not happening. Right? So some of our answers talked about how a transformer works with AC, and they gave a really good explanation of how it worked with AC, and then they were like, oh, with batteries it doesn't work like that. Or with DC, nah. You want to talk about what happens when you put actual DC on there. And then like make a few notes along the way saying like why that's not the best and how it would be different if we were using the correct way of doing this. Right. Okay, so we have EMF is only generated when there is a changing flux. Hence, no EMF is produced in the transmission circuit. And you could probably stop there and just say, therefore, no power is available to the farm. So if there's no power being given to the transmission circuit, then there's none that's going to go all the way to the load circuit. You could put in an extra sentence there saying that if you wanted to, but that's probably enough to get you the marks. What we're really looking for there for the 3 marks is that the DC current creates a constant magnetic field. That means you've got a constant magnetic flux. And then the last thing is that we don't get an EMF if we've got a constant flux. We need a changing flux. Yeah, so that's why the farm doesn't have any power. All right. Estelle closely examines the primary coil of a step-up transformer. She looks at it, touches it, smells it, etc. What will she notice? I probably could have phrased this question better. What I'm looking for here is like, what would she notice that she wouldn't notice if we hadn't done this thing with the batteries? So what's happening in an ideal transformer is, when we're using AC and everything's running correctly, is that all the energy that's getting produced by this generator over here passes through here, and all that energy gets passed across from one side of the primary coil to the secondary coil and then goes into the transmission circuit. But when we use DC, none of that energy is getting passed across, which means all the energy has to get dropped somewhere in this circuit here. Right? And given that the only component in that circuit is the primary coil there, all that energy is going to get dropped in the primary coil itself, not passed along from the primary coil, but actually dropped inside the primary coil. So that coil is going to get very hot, or make a lot of noise, or something. It's going to act as a load in the circuit, right? So we're looking for something. A lot of energy is being lost here. Anything that makes the point that a lot of energy is being lost here is being dumped on this primary coil, it will be hot. When in doubt, the type of energy, if you don't know what type of energy is being produced, heat is being produced. That's the sort of the random type of energy. Okay. Question 15. Estelle doesn't realize her mistake. She thinks it might be the iron core of a transformer, which is damaged. So she thinks that there's a problem with the transformer itself. She tries to remove the coil, but finds it more difficult than she'd expected. She realized that this must be due to eddy currents in the iron core, which is correct. Show step by step how to find the eddy currents in the iron core as it's removed from the coil. Now, I thought everyone was really going to struggle with this, and I was really pleased with the way you went about this. It was very well done overall. Most people, or a lot of people, got 2 out of 3, and a lot of people got 3 out of 3. And what I was really pleased with was the way you structured your answers. Some people were drawing me lovely diagrams, this happens, and then that causes this next diagram, etc. I'm just going to do it with words, but I love those diagram ones. But yeah, so we want to work through, and just along the way, you want to pepper it with the right terminology. So you want to make sure you're using words like lens, Lens law, maybe induction, Faraday, eddy currents, things like that, just to show the examiner that you're au fait with the terminology. Okay, so the thing we're trying to explain is, or the thing we're trying to get to is whether the eddy currents are going clockwise or whether they're going anti-clockwise. Okay, so first off, we better work out what we've got here is an area, and we've got a magnetic flux through it maybe, but I can't see any magnetic field lines on here. So we better work out what direction is the magnetic flux pointing. Okay, so let me do some dot points. Let me call it the initial magnetic field through the area of the iron core points, well, I might structure this as a question. What points in which direction? All right, and then we'll answer that, and then we'll move on. All right, so we're going to use our right-hand curl rule for that. So if we look at the, I'm not sure if my webcam is actually inverting the image here, so I might be using my left hand according to you here, not 100% clear. But if we look at that diagram there, we've got a current which is going around clockwise in our view. If we use our right-hand curl rule, we'll see that that means that we're actually standing at the southern end of that magnet, which means we have magnetic field lines which are going away from us. They're going into the page. So right-hand rule tells us that the magnetic field, and let me call it B0, points into the page. Right? Then we're going to try and removing the coil. So removing the coil is going to mean we're going to have less of that magnetic field, less flux from that magnetic field B0. So removing the iron core upwards means less of this into the page flux. All right, and that's into the page flux is a little bit of a loose terminology. I've never quite worked out the best way to put that, because flux is supposed to be a scalar, but we all know it's kind of got a direction on it. So it's an into the page flux, and we've got less of it. All right. Lens law tells us that induced currents will form which produce, and we're just going to state Lens law here really. So Lens law tells us that induced currents will form which produce a magnetic field which opposes the change in flux. Okay, so if we've got less into the page and these currents are going to oppose that, this means they will produce a field into the page. Okay, so they're going to make up for the loss of that into the page flux. Right. And then we just say, well, what type of current produces an into the page field? Well, we actually already worked it out. We've already got it on that diagram. That current going clockwise produced an into the page field. So if we want more into the page fields, then we need a clockwise current. So right-hand rule tells us that these currents must be clockwise. Okay. Some people did it an even what I consider a more complex way, but if it made more sense to them, then that's absolutely fine. They said that, well, if we're pulling the coil outwards, then we need to produce a force inwards. And if we're producing a force inwards, then that's going to be a magnetic force. And they said, well, the solenoid itself, that's got a southern end close to us. And if we need a force pulling back inwards, then we need the iron core to have a northern end at the other, close to the solenoid as we pull it out. And then they said, okay, well, if we treat the iron core as a bar magnet, what sort of eddy currents do we need inside to create a north end where we need it? Went through the whole process. If you did that, I really, really appreciated if you redrew the diagram from that angle there, so we could start labeling north, south, etc., and start pulling things apart. Oh, that doesn't look too good, does it? Just so that I could see exactly what you're talking about. In all these right-hand rule questions that involve FBIs and all that sort of stuff, it does get really confusing writing it out. And even the way I've written there, I'm sure is not perfectly clear to everyone. So diagrams are super helpful, just to be really clear, and like you can refer to your diagram in your explanation. It is really hard to follow three-dimensional directions in words, into the page, outwards, pulls outward, what does this mean, blah, blah, blah. Diagrams are super helpful, especially if you're going to sort of do some mental rotation in there and start talking about what you see when you pull it out, etc. Draw a diagram. You don't have to be the best artist in the world. Draw a diagram. Okay. Yeah, I think that was the end of our induction, and then we're going to move on to special rel. Okay. So our special relativity question was a pretty standard rocket ship type affair. So, seeing her struggles, Estelle is picked up by a pair of friendly aliens who are observing the Earth from afar. They agree to take her on a hyperspeed joyride through the solar system, and they travel to the aliens' home base on Jupiter at 200,000 kilometers per second. Estelle measures the journey from Earth to Jupiter to be 600 million kilometers. What distance does mission control on Jupiter measure the journey to be? So the thing that cost a lot of people marks on special rel, and it's not just question 16 that sort of goes through the whole of them, is just being unclear about the fact that neither of them is correct. Neither of them is the proper, in the sense of correct, observer. Both Estelle, who's on the rocket ship, and Mission Control, who's stationary on Jupiter, have their own frame of reference. And if Estelle's not accelerating, then both those frames of reference are inertial, which means they both make perfectly valid measurements about the world. So when we say something like a proper measurement, we're talking about who is in the right position to make that particular measurement. So in a given scenario like this, you might make 3 or 4 different measurements, and for different ones, different people might be the proper observer, right? So if I'm, for instance, playing with my yo-yo right here, then I'm going to be the proper observer of that, because those events are happening right in front of me. If I'm measuring the distance between Earth and Jupiter, but I'm moving with respect to Earth and Jupiter, then I'm not going to be the proper observer. Okay? So in this first question here, we do need to be really careful. We're going to write down, okay, yeah, start by writing down L dash equals L naught divided by gamma. Great start, and you probably got half a mark or something just for writing that. But that's not the work here. The work is not writing down the equation or even finding gamma or anything like that. The real work here is working out which one's L dash and which one's L naught. Okay? Now before we get there, let's work out gamma, and it's worth stating it explicitly. So gamma is going to be equal to 1 on the square root of 1 minus v squared on c squared. So that's 200,000 kilometers per second divided by 300,000, I put one too many in there, kilometers per second. And then all of that is squared. It's v squared over c squared, not just v over c. And a few people forgot to square, which was a little bit unfortunate. Tiny little mistake can cost you there. And it looks really ugly like that. Right, now, look, this is, I keep on banging this drum all year, but if you don't put units in your calculations, then you're gonna make mistakes. So a lot of people put 200,000 here, and they put 3.0 times 10 to the 8 down here, because that's what they know the speed of light is. And if you do that, you're gonna stuff it up, because 3.0 times 10 to the 8 is meters per second. This is 200,000 kilometers per second. If you're not working with units in your calculations, then you are costing yourselves marks time and time and time again. Now, this particular SAC didn't punish you very much for it, because there's not quite as many formulas in this SAC, but we saw it once again with this question. People who are not putting units in are shooting themselves in the foot. Anyway, if you do that correctly, and if you do put the right units in, then what you get is 1.34 there. Some people they got the right number there, 1.34, and if they did everything else right and used it correctly, then they got the full 2 marks without ever stating it explicitly that the number they got was 1.34. But if you got that number and then went on to make some mistakes, you could still get some marks just for getting that number right. In fact, there was a whole mark allocated just for calculating gamma correctly. So if you're not working through questions slowly, writing down your thinking on the page, writing down, okay, gamma is 1.34, then you're potentially costing yourselves marks. So make sure that you are explicitly writing down what gamma is in every special rel problem. There's usually a mark allocated for it, and even if there's not, just having it there on the page makes it easy for you, because you're going to use it again and again and again in each part of the question. Okay, so we got 1.34 there, but then the real work begins. We have to work out who's the proper observer here. Well, the proper observer's length is, well, my personal test for it is who can take their sweet time to do the measurement, right? So if we think about Estelle, she's on Earth, Earth blows past that way, and then Jupiter's coming at her, and Jupiter comes here, and then she goes, oh, the distance is between there and there. Whereas the person on Jupiter, they're stationary with respect to Jupiter and the Earth. They can get out a laser beam and they can bounce it off a mirror on Earth and they can wait for it to return, or they can get a big ruler out and they can size it up, or they can do some sort of angular, nonsense with working out how far away it is. They've got all the time in the world to make that measurement, because the Earth's not going anywhere, according to them. So Jupiter is the proper observer of that distance, right? Jupiter is the one for whom Jupiter and Earth are sitting stationary, and they can measure the distance between them in what we call the proper length. Okay, so Jupiter is L naught. So L naught is actually the thing we're trying to find here, which means L dash, Estelle's measurement, is the other one, right? The one that's Jupiter and the Earth are both moving with respect to Estelle, so she is going to see their length contracted. She's going to see the smaller version of this length. So just rearranging that equation, we get 1.34 times 600 million kilometers, and 1.34 times 600 is 804. So we get 804 million kilometers. Right? Bigger than. So remember, when it comes to length, the person who is moving with respect to the length in question is going to measure the shorter distance. Estelle is moving with respect to Jupiter and Earth, so the distance between Jupiter and Earth is going to be smaller for her than it is for the person who's stationary. Okay. Question 7. Question 17 was a bit of a trap. Sorry about that. It was a bit sneaky. She tries to calm her frayed nerves by playing with the yo-yo throughout the journey. She counts that she's dropped and then caught the yo-yo 200 times. How many times did the Jupiter observers say she caught the yo-yo? This one is trying to tempt you into doing some time dilation. But catching a yo-yo is not an amount of time. Catching a yo-yo is an event. And all observers agree on the events. So if I say I caught a yo-yo twice, you, a different observer, have to agree, yes, you caught the yo-yo twice. Now, you might say that took 5 minutes, and I might say it took 30 seconds, and you might say the first one took ages and the second one took less time, or we might disagree about time lengths between events, and we might disagree about how long the string on the yo-yo is and so forth, but we're not allowed to disagree about whether something happened or not. So if I say something happened 200 times, you have to too, which means the Jupiter observer has to observe 200 yo's of the yo-yo. Okay, question 18. On one throw, Estelle gets the yo-yo to sleep for 35 seconds, beating her previous record of 32 seconds. How long do the Jupiter observers measure the sleep to last? Now, this is once again a question of who's the proper observer of this, who's the improper observer, who's the T dash and who's the T naught. Well, Estelle is holding the yo-yo in her hand. She puts it down here. From her point of view, the yo-yo just moves downward slowly, comes up slowly. Everything's happening as if it's just in a lab in a room. According to the Jupiter observers, the dropping of the yo-yo happens here, and then it hits its nadir down here, and then it comes back up to here. It's moved thousands of kilometers in that space of time. In 32 seconds, it's gone millions of kilometers, right? They're not going to have the proper observation of that time. So Estelle is T dash, that 35 seconds is, Estelle is T naught, that 35 seconds is T naught. The Jupiter observers are going to have a T dash. So we're going to have T dash is the thing we're looking for, and it's going to be 1.34 times 35 seconds equals 46.9 seconds. Okay. I think that's right. Hold on. That's about right. So the important thing, once again, it's not about whether you can write down the formula, it's not about whether you found gamma correctly, it's about whether you're correctly allocating the T dash and the T naught. Who is the proper observer of this thing? Okay. All right. Lastly, question 19, another bit of a trick. I feel like I should apologize for this, but I'm not going to. Really hard one, and actually what I found was a lot of students who did really well in the rest of the SAC, like incredibly well, this is where they fell down with this one. So we know that mass dilation is a thing, but that doesn't mean it's always a thing, okay? So let's go through this. Estelle claims that her yo-yo seemed heavier than usual during the journey. She thinks that maybe that's why she was able to achieve a better sleep time than usual. Kroglon 5, her alien companion, thinks that she must be imagining things. Does Einstein's theory of special relativity support Estelle's theory? Explain. Okay. Let me tell you the way I wanted to answer this, the way I was going to answer this, and then I'll tell you the way that some of you guys did, which was way better than my answer. So my answer is that the dropping of the yo-yo is something that happens in Estelle's frame, or the yo-yo is moving at the same speed as Estelle. So Estelle's measurement of the yo-yo's mass should just be as if v equals 0. It should just be the yo-yo's rest mass, because the yo-yo is stationary with respect to Estelle. So let me say that. The yo-yo is stationary with respect to Estelle. Hence, Estelle's measurement of its mass should be its rest mass. Okay. So there's nothing relativistic going on there, right? There's a yo-yo that's sitting in front of Estelle, and she's measuring its mass, and it's just sitting there. And then, okay, maybe it's moving when she drops it or whatever, but it's moving at regular speeds, not relativistic speeds, right? Hence, there is nothing relativistic going on here. Estelle is imagining things. Okay, so it's only worth 2 marks, so we don't have to sort of belabor the point too much. Imagining? Yeah, imagining. Okay. Wow, imagining is an ugly word. Anyway, but you guys came up with a way better answer, right? A lot of you guys actually went back to Einstein's postulates, and you said you noticed one of Einstein's postulates, and I'll write it here. Einstein's postulate: the laws of physics are the same in all inertial reference frames. Okay, so you said, okay, the laws of physics are the same in all inertial reference frames. Estelle might be traveling across the universe at 200,000 kilometers per second, but she's in an inertial reference frame. So the laws of physics should be the same. So when she drops her yo-yo, it should be exactly the same as when she drops her yo-yo when she's sitting in a lounge room at home. All right. Let me just try and punch that up into an answer. Estelle is in an inertial frame when measuring the yo-yo's mass. Therefore, she should measure, or when, hold on, the inertial frame when conducting the sleep time experiment. We call everything an experiment regardless of whether it really is. Estelle is in an inertial frame when conducting the sleep time experiment, so should not notice anything different from doing this on Earth. Okay, and so she's imagining things. Kroglon 5 is correct. The thing that this really drew out this question, the thing that this made clear, is whether you are fully bought into Einstein's idea that there is no correct reference frame. The people who were like, yeah, she's traveling fast, therefore it should be heavier, there's still a remnant in your mind of really the Jupiter observers are right. They're the ones who are sitting still and Estelle is moving, right? But what Einstein asks you to do is to get rid of that thinking, that there is no such thing as absolute velocity, that Estelle is just as stationary as anybody else in the universe. As long as she's not accelerating, her inertial frame is as good as anyone's. And in that case, everything about the yo-yo situation is the same as if she was doing it in her bedroom. Okay? But it requires that radical rethink that there's no one who's like, right, there's no God's eye view here. There's just everybody's frame, everybody's measurements. And once you realize that, then you start thinking, instead of thinking, oh, the yo-yo is moving, you think the yo-yo is moving according to who? And then you say, okay, well, according to Estelle, the yo-yo is not really moving very fast, in which case there should be no mass dilation, etc., etc. Okay? But it's really important that you can get your head around that. It's really important that you can be like, I'm going to remove this idea from my head. There is no correct frame in the universe. All right. Thanks, guys. I'm really proud of the way you've done this whole SAC overall. I was very impressed with the special relativity part in particular, and also with some of your answers around lens law and stuff. Really, really good work. I'll see you back at school in a few days. Bye.